If you consumed any amount of YouTube content about evolution, including many of the most popular biology educators, you've heard the phrase punctuated equilibrium. It was most likely described to you as a pattern of stasis and rapid change, and that there was nothing at all radical about it. In 1982, leading population geneticists wrote a piece titled A Neo-Darwinian Commentary on Macroevolution, published in the journal Evolution. In it, they write, quote, "It does not appear to us that the theory of punctuated equilibria should be accepted as a major revolution in evolutionary biology, and that, quote, we do not feel logically compelled to abandon neo-Darwinism in favor of the theory of punctuated equilibria." Why do these guys seem so defensive? Isn't punctuated equilibrium just a pattern in the fossil record? Doesn't it just reflect rapid natural selection that isn't preserved in geological time, and therefore doesn't fundamentally challenge what we know about population genetics and speciation? If that's what you've been told, then this video is for you. The central thesis of this video is that punctuated equilibrium, as commonly presented today, is a bastardized version of Gould and Eldredge's original theory, that they saw their theory as fundamentally challenging the modern synthesis. Indeed, they likened it to a major revolution in biology that not only recognized patterns, but sought to erect new processes to explain those patterns. So let's dig in and find out what punctuated equilibrium was really all about, and ultimately why it's largely rejected today. Before we can discuss Gould and Eldredge's critique of the modern synthesis, we must first understand what it is. You may have heard it described as the merger of Darwinian natural selection and Mendelian genetics, which is true, but that doesn't really tell you a whole lot. Shown here are the 5 tenets of the modern synthesis. First is that genetic variation is the source of phenotypic variation. Second, that variation arises due to mutations that are random with respect to their impact on fitness. Third, accumulated mutations selected over time are the basis of evolution within a taxon, i.e., gradualism. Adaptation is solely the result of natural selection, and 5, that evolution occurs at the population level. These 5 tenets have important implications. Firstly, they effectively link micro and macro evolution. To the modern synthesis, there is no distinction in the fundamental processes that are occurring at these different levels. Of course, this does not mean we can't observe macroevolutionary patterns, but these patterns are ultimately the results of population-level processes. The modern synthesis has had many critics throughout the years, from Goldschmidt's hopeful monster mutationist theory, neo-Lamarckism, and most recently, the so-called extended synthesis. But none has been more forceful or long-lasting as punctuated equilibrium. So influential was the rhetoric behind it, but not the science, as I'll soon show, that you have certainly heard your favorite YouTuber use punctuated equilibrium as if it is some accepted scientific theory. Spoilers, it was rejected in the 70s and 80s, and it's still rejected today. The concept of punctuated equilibrium first appeared in a 1972 book titled Models in Paleobiology, the 5th chapter of which was written by paleontologists Niles Eldredge and Steve Gould. In this chapter, they propose that the general patterns of evolution in the fossil record is stasis with subsequent rapid, geologically speaking, bursts of speciation. In this chapter, they propose that speciation is mostly caused by small, isolated populations that are generally unlikely to leave representatives in the fossil record, and thus, when the population grows large enough, what we observe is an apparent immediate change in phenotype. Initially, this idea was not overly radical. There were debates about the magnitude of changes you'd expect to see and whether the fossil record was complete enough to rule out strict gradualism, but nothing about the 1972 book chapter fundamentally challenged the modern synthesis. But where the 72 paper was vague, Gould and Eldredge 1977 was not. In this paper, they made several radical claims that, to them, fundamentally challenge the tenets of the modern synthesis. These claims would be expanded and clarified by Gould and others, including Elizabeth Verba and Stephen Stanley. Indeed, Gould's last major work, The Structure of Evolutionary Theory, is a 1,000-page beast that lays out in excruciating detail what he saw as the failure of the modern synthesis. In short, they saw the modern synthesis as being incapable of explaining trends in the fossil record, that wholly new mechanisms existing at the macroevolutionary level would need to be invoked, i.e., macroevolution was not just repeated rounds of microevolution, a phrase used by Irwin in 2000. Now, punctuated equilibrium sought to explain three key patterns: stasis, the association of morphological change with speciation, and phylogenetic trends. Again, they saw these things as being unable to be explained by microevolutionary processes alone. The theory of punctuated equilibrium posited that stasis was the result of developmental constraints, limiting the direction of natural selection. In 1981, Gould mischaracterizes the modern synthesis as being unable to account for this, likening the view of organisms in a synthetic viewpoint as spheres that are infinitely moldable. Many authors at the time, including leading population geneticists such as Brian Charlesworth, Russell Landy, Monty Slotkin, Joe Felsenstein, and many others, noted that this was a gross mischaracterization of the modern synthesis. At least as far back as Muller, writing in 1949, proponents of the modern synthesis were aware that organisms are constrained by development to some degree. Furthermore, developmental constraints as an argument for stasis ignores that artificial selection, an inherently microevolutionary process, has radically changed body plans in a very, very short period of time. The classic example is the diversification of the mustard plant into kale, broccoli, Brussels sprouts, cabbage, kohlrabi, and cauliflower. Thus, if variation exists for natural selection to act upon, even if that variation is rare and may not be preserved in the fossil record, if it becomes favorable, it can rapidly fix within a population. Stephen Stanley argued that stasis was also explained by gene flow, invoking Sewell Wright's famous result that even one migrant per generation was enough to prevent differentiation. However, Stanley ignored the fact that Wright was writing about neutral alleles, that natural selection can and does drive differentiation even in the face of gene flow. Is there a good alternative explanation for stasis in the fossil record using purely microevolutionary processes fully within the scope of the modern synthesis? Of course. Population geneticists in the 80s argued with Gould that the pattern could be explained by stabilizing selection, the idea that there is a mean phenotype within the population that is most fit, and selection acts each generation to remove individuals that deviate too far from this mean. In a large-scale study by Estes and Arnold in 2007, they fit a range of evolutionary models against phenotypic divergence patterns across a phylogeny that spanned hundreds to millions of years. These models included stabilizing selection, genetic constraints, as well as purely neutral evolution. They consistently found that stabilizing selection was the most explanatory model, and that across a wide range of heritability values, genetic constraints had minimal impact on model choice. Again, this is in accordance with what we've seen in nature. Organisms are rarely restricted by variation itself. Developmental constraints supposes that certain variation just can't arise, whereas stabilizing selection suggests that it doesn't increase in frequency because it isn't beneficial, but it may remain at low frequency as a neutral or mildly deleterious variant until a shift in the environment shifts its fitness effect. This is exactly how herbicide and antibiotic resistance has been shown to arise. In pest populations, the variation for herbicide resistance has been found to be segregating at low frequencies prior to exposure to the herbicide. In short, developmental constraints is a poor predictor of patterns of macroevolutionary change. Instead, shifting fitness effects across an ever-changing environment better explains stasis in the fossil record and is completely compatible with the modern synthesis. What about the supposed association of morphological change with speciation, a key tenet of punctuated equilibrium? Let's introduce some jargon. There are two types of change that can occur in a lineage: anagenetic and cladogenetic. Anagenetic change is heritable change within a lineage across successive generations. If this sounds like the definition of evolution, it's because it is. It's how we understand evolution from a modern synthetic view. Punctuated equilibrium rejects this view. Instead, it asserts that there is virtually no anagenetic change. Remember, because developmental constraints restrict it from happening, and that instead all change is cladogenetic. Cladogenesis is change associated with the origin of new lineages, or lineage splitting. Supporters of punctuated equilibrium argue that speciation events themselves were drivers of morphological change. This is not at all the view of the modern synthesis. Speciation, by which we mean the accumulation of reproductive barriers between descendant lineages, is not itself favored by any force or itself a force capable of causing change. It is a byproduct of the microevolutionary forces of natural selection, genetic drift, and mutation occurring within those descendant lineages. To Gould and supporters, since developmental constraints were so strong, the only way for populations to overcome them is to go through a massive bottleneck. To understand this, let's introduce an idea by the famous population geneticist Sewell Wright called the shifting balance theory. In this theory, you can imagine a population occupying an adaptive peak, surrounded by valleys of low fitness. Selection restricts the population from ever leaving the peak and moving to a different peak because this would require first a loss in fitness. However, if the population undergoes a bottleneck such that selection is weakened, the population can rapidly shift to a new adaptive peak. Ernst Mayr extended this idea into what he called genetic revolutions. The idea that these bottleneck populations would experience a grand reorganization of their genome that would drive rapid evolutionary novelty. Gould and others latched onto this explanation as the mechanism for the association between speciation and morphological change. Several issues emerge with this as an explanation of speciation as a driving force behind morphological change. Matt Pinnell and colleagues in 2014 lay out these difficulties as follows. One, that associations between speciation events and rapid change requires the strong assumption that we've sampled ancestors and their direct descendants, which is incredibly unlikely. Two, it assumes that the fossil record is exceptionally well sampled, thus such that we can rule out gradualistic evolution. This brings up an important point, that the timescale of relevance to the geological record is quite different than that of the organism of interest. Nearby strata may record millions of years of separation, which, depending on the generation time of the organism in question, could represent many millions of generations of change. And thirdly, to test this association, we need to make strong assumptions about the taxonomic designations we're using. This last point, as noted by Levinton and Simon in 1980, introduce a tautology. Identifying change in the fossil record necessitates a new species description. Thus, any change in the fossil record will correlate with a speciation event. Just as problematic is the recognition, thanks to advances in molecular genetics, of cryptic species, morphologically indistinguishable but genetically distinct species. This kind of change is completely invisible to the paleontologist. Finally, Mayr's ideas of genetic revolutions falls flat on its face when examined theoretically. Mayr, as well as Gould, had a tendency of making verbal arguments with little to no mathematical underpinning. Indeed, Mayr famously critiqued population genetics as beanbag genetics, and that the works of Fisher, Haldane, and Wright had contributed little, if anything, to the study in natural populations. See Haldane's excellent paper In Defense of Beanbag Genetics, in which he eviscerates Mayr's silly critique. Nick Barton and Brian Charlesworth in 1984 evaluated Mayr's supposed mechanism mathematically, noting that founder events were incredibly unlikely to drive rapid adaptation or so-called genetic revolutions. These revolutions are supposed to rely on genetic drift to shift populations between adaptive peaks, but Mayr and Gould failed to recognize that genetic drift is incredibly slow. It occurs at a rate of 1 over the population size and takes, on average, 4 times the population size in generations for any variant to reach fixation. This is too slow to cause the supposed rapid morphological change that punctuated equilibrium seeks to explain. Now, if genetic revolutions were responsible for rapid evolutionary change, we would expect to find evidence that bursts of evolution correspond to population bottlenecks. In the 1980s, Alan Templeton showed that for the radiation of Drosophila and the Hawaiian Isles, that no reduction in heterozygosity was found, indicating that the radiation had not proceeded via repeated bottlenecks, as punctuated equilibrium would predict. Furthermore, the existence of ring species, in which semi-isolated populations gradually accumulate reproductive isolation with distance, completely undermines the notion that genetic revolutions are necessary at all. Isolation can accumulate quite gradually. Indeed, I showed in a 2022 paper using simulations that when population isolation occurs via repeated colonization and founder events, underlying gene tree discordance, called incomplete lineage sorting, is greatly reduced compared to when populations split via allopatry in previously large ancestral ranges. Thus, if Mayer's mechanism were true, we should see bursts of rapid evolutionary change corresponding to high gene tree concordance. Of course, the exact opposite is seen. Perrins, Ficucci, and colleagues in 2021 showed that across the tree of life, the most rapid evolutionary change corresponded to the most gene tree discordance, not the least, meaning that bottlenecks could not explain rapid morphological radiations. Thus far, punctuated equilibrium has been wrong about the mechanism of stasis in the fossil record and about a believed, but unsupported, association between morphological change and speciation. The last major point that Gould and others made was about phylogenetic trends. A central argument of punctuated equilibrium, as stated previously, is that microevolution is insufficient to explain macroevolution. Punctuated equilibrium posited the following to make their argument. First, morphological change is associated with speciation, which we've already shown is faulty at best, tautological at worst, and two, that the direction of change is random with respect to the direction of macroevolution. To understand their argument, imagine lineages themselves as the individuals, with the clades they belong to as the population. Each time a lineage splits can be thought of as a birth event, and since morphological change occurs only at the split, the new lineages have some traits not before seen in the population. In this way, they suppose that selection can then act on a trait at the lineage level, such that any trait that promotes subsequent births, i.e. splitting events, will be favored. This is called species selection, and it goes back to at least R.A. Fisher. Species selection, they suppose, decouples micro and macro evolution, since it's inherently a macroevolutionary mechanism that is not experienced at the micro level. However, this concept has several serious flaws. The most serious is that it completely relies upon the claim that cladogenetic change is more prevalent and important in evolution than anagenetic, which Gould and friends suppose to be basically non-existent. Second is their claim that this change could be random with respect to its impact on macroevolutionary trends. This randomness is necessary for species selection because if morphological change is not random at the species level, i.e. is driven by natural selection within the population, then species selection is describing nothing more than a higher level pattern that is emerging from processes acting at the level of the population. One pattern that species selection sought to explain was parallelism, the observation that two lineages might acquire the same trait convergently. Obviously, microevolutionary processes are well equipped to explain parallelism. A prime example is the convergent evolution in the white sands lizards, in which three different species each acquired the same white phenotype independently via different amino acid substitutions. On a similar note, rapid morphological change can occur via ecologically driven character displacement, a phenomenon again explained by microevolutionary processes of conspecifics. As an example, detractors of punctuated equilibrium in the 80s used niche partitioning in anolis lizards in the Caribbean, with each species rapidly diversifying to occupy different parts of the canopy as an example. In this way, natural selection is acting upon variation at the population level to specialize subsets of the population to different available ecological niches. No need to invoke selection above the lineage level. As mentioned above, the widespread occurrence of cryptic species undermines punctuated equilibrium's central tenet that cladogenetic change is the most important feature of evolution. Many cryptic species arise following vicariance, in which a historical range is divided by some natural phenomenon such that the ecological conditions on either side are not different, and the two populations evolve gradually away from some ancestral genotype, but display very little morphological differences since the environment itself has not changed. It is unknown how often this type of speciation occurs, but it has become increasingly appreciated over the past decade. Lastly, species selection suffers from a theoretical issue, and that the efficiency of natural selection is dependent on the number of replicators on which it can act. In a microevolutionary context, this is individuals in a population. For species selection, this is specific lineages within a clade. Obviously, the number of individuals within each lineage is necessarily greater than the number of lineages. Thus, natural selection will always be more efficient at the individual level than it is at the species level. In fact, unless the species-specific trait that promotes diversification is extremely strong, random lineage drift, an analog to genetic drift, should dictate patterns of diversification more than species selection. This is akin to how genetic drift dominates allele dynamics in very small populations. To sum up, punctuated equilibrium proposed that stasis was the result of developmental constraints that severely restricted the directional natural selection. These developmental constraints could only be overcome by first a severe bottleneck, followed by a genetic revolution that rapidly ascended a population up a new adaptive peak. This genetic revolution occurred during cladogenesis, leading to an association of morphological change and speciation events, and leading to the supremacy of cladogenesis over anagenesis in evolution. Finally, since the direction of change is random following speciation, species selection could act upon lineages with greater diversification rates, leading to patterns of parallelism and convergent evolution. Each of these points have been thoroughly debunked, both in the 1980s and with modern research. Stabilizing selection, a population-level process, better explains stasis in the fossil record, that speciation and rapid radiations do not correlate with population bottlenecks that are supposedly required to overcome constraints, and that ultimately speciation is not a cause of evolution, but a result of it. And finally, emergent patterns at the phylogenetic level are the result of processes occurring within populations. Despite the obvious failings of the theory of punctuated equilibrium, it generated such fervent discussion and was promoted by one of the greatest science popularizers of our time, Stephen Jay Gould, that it was destined to enter the public's lexicon, regardless of if its usage today is a mere shadow of its original breadth. Today, punctuated equilibrium means simply stasis followed by change. So watered down is this that rapid change does not even mean necessarily cladogenesis, but could just mean rapid with respect to the geologic record. In many ways, people use mechanisms of the modern synthesis to explain this pattern, while still calling the pattern punctuated equilibrium. I suspect Gould rolls over in his grave every time his theory is employed in this way. Every decade or so, radical new ideas are put forward that are supposedly going to overturn the modern synthesis. In 1986, Don Rosen wrote, "There is no need to placate the ghost of neo-Darwinism. It will not haunt evolutionary theory much longer." Similar claims were made by Gould, Verba, Stanley, and others in the 70s and 80s. Today, the extended synthesis supporters are regurgitating many of the same tired arguments that were made in the 80s, that microevolutionary mechanisms of the modern synthesis are incapable of explaining epigenetics or developmental biology, niche construction, etc. All the while failing to recognize that each of these topics were investigated by supporters of the modern synthesis as early as the 1940s. There has never been an adequate replacement for the mechanisms of natural selection, genetic drift, gene flow, and mutation as the driving forces of evolutionary change. This is because these processes are fully capable of explaining population level processes. And it's these population level processes that ultimately drive macroevolutionary patterns. In reviewing Rosen's 1986 book, Joe Felsenstein famously wrote that, in the end, we're still patiently waiting for a post-neo-Darwinian theory that has not appeared. Thanks so much for being here. Hope you learned something new about punctuated equilibrium. And the next time somebody says it's just a pattern in the fossil record, point out that Stephen Jay Gould would be quite displeased to hear that. See you next time.